talk about exponential equations. We took a look at one a little while ago. Some exponential equations can be solved very easily in your head. For example, this one here, 2 to some power is equal to 16. That's pretty easy to solve in your head, right? X has to be what? X has to be 4. Because 2 to the 4th power is 16. Okay? Those are not the type of exponential equations we're going to be doing. Because what if, and I think the one we looked at was, what if I asked you 2 to some power is equal to 5? Or it was something similar to this. You can estimate, you can get pretty close. 2 to what number is going to get you close to 5? Something larger than 2, but smaller than 3. Closer to what number? 2 or 3? Closer to 2, because 2 squared is 4, 2 cubed is 8, so it's going to be a little bit closer to 2. So we could estimate and say, well, maybe this is about 2.2, or maybe it's about 2.3, something like that. But how do we find out for sure? What's the opposite of an exponential function, or the inverse of an exponential function? Logarithms. That's why I've been studying them together, because they're inverses of each other. Okay? So let's do an example. Example 1. After you write down these steps. Steps for solving exponential equations. They are very easy steps. And there's only 3? Yeah, there's only 3. Step 1. Isolate the exponential term. The exponential term consists of the base and the exponent, not the coefficient. If there's a coefficient in front of the exponential term, you got to get rid of that as well. Isolate the exponential term. Okay? Second step is to use a corresponding logarithm. What does a logarithm do, by the way? It cancels the base. Because we want to get rid of the base so we can deal with that exponent, because the exponent is the variable. So logarithms will cancel the base. And step 3 then is to solve for the variable. Whatever the variable is, doesn't have to be x. Usually it is, but doesn't have to be. So, example 1, part A, 3 to the x minus 2 minus 4 is equal to 2. So first they have to identify the exponential term in order to isolate it. The exponential term consists of the base and the exponent. So this right here, 3 to the x minus 2 power, this is the exponential term, 3 to the x minus 2. That needs to be isolated. It needs to be all by itself. So you're going to add 4. Very good. Add 4 to both sides. So now we have 3 to the x minus 2 is equal to 6. Now, on step 2, this can be done a number of ways. What specific logarithm cancels a base of 3? Log base 3. So I'm going to show you this way to do it, and then I'm going to show you another way here in a second. You can do a log base 3 on the left and a log base 3 on the right. Okay. The reason for using a log base 3 is because the exponential has a base of 3. Those cancel each other out. So what you're left with is the equation x minus 2 now equals the log base 3 of 6. So that was step 2. We used logarithms. Logarithm canceled the base. If there's no base, that means this x minus 2 is no longer an exponent. It's just an expression, x minus 2. Step 3 is solve for the variable. The variable now is subtracting, there's a 2 subtracting from it, so we have to add 2. Initially, some students get a little confused on what to do on the right side. Where do you add the 2? It has to be outside or after, because this 6 is considered to be inside of a logarithm function. You can't add anything to it. You can't subtract anything from it. Okay, the log base 3 of 6 just stays log base 3 of 6, and then you add the 2. So your final answer is x equals log base 3 of 6 plus 2. Yep. This is called exact form. We have to leave it in exact form. In order to find out the approximate answer, we'd have to use a calculator. We don't use calculators. We're much too smart for that. So we leave the answer in exact form. Now, if you were to use a calculator, because next year in calculus, you may have to turn this into the approximate answer and not the exact answer. So how would you use a calculator on this? It's good to know. You got to do the change of base. Remember that from last time? Most calculators do not do log base 3. They do a log base 10 or natural log. So even though we aren't going to use calculators, I'm going to show you how to use it, because in your AP Calculus class next year, which you're all taking, by the way.
No choice.
I will sign you up for AP Calculus.
I think that's our choice.
No.
Hey, that's like my calculator.
Not a song.
Okay, anyway. To do the change of base formula and to evaluate this, you have to change the base on the log base 3 of 6. That turns into the log of 6 over the log of 3 plus 2. And then you type that into your calculator. So where'd you go? There you are. So log, my calculator's frozen. There we go. So log 6, divide that by log 3. Make sure you close your parentheses on your calculators too. Then hit enter. Then add 2. So the approximate answer is 3.63 using a calculator. Now, I don't know if you caught this last time, but I did say it as we were leaving. Do you have to use change of base with the log base 10? Remember what I said last time? You could also do the change of base formula with a natural log. If you had used this ln button, natural log of 6 divided by natural log of 3, and then you can add, well, let's see, I'm going to add 2 afterwards. Hit enter, then add 2, 3.63. So using the change of base formula works with either the common law or the natural log. Okay? This is what you would be expected to do if calculators were allowed. But since they are not, you leave it in this exact form. You following? Okay? So that's one way to do it. Here's another way that would be perfectly acceptable. I'd accept this way as well on a test. Let's go back to the original problem. So this is version 2. We have 3 to the x minus 2 equals 6. Other 1050 classes may do it this way because calculators are allowed. If you were using a calculator, you might want to do it this way. Yeah. Instead of using a log base 3, because we would be using calculators using this method, why would I want to avoid a log base 3? Most calculators don't do them. What if I just did a plain natural log? Does a natural log cancel a base of 3? No. So why would I want to use a natural log? Because it works on a calculator, true, but it still hasn't canceled that base. So have we gotten anywhere? What rule of logarithms or laws of logarithms did we learn about last time? Dealing with powers, where can the power go?
Move it down. You can move the x minus 2 down.
We can move the x minus 2 down in front of that. So now we have x minus 2 times the natural log of 3, and that equals the natural log of 6. So you seeing where this is going now? We're trying to isolate this x minus 2. It's being multiplied by the natural log of 3, so how can you get rid of it? Divide by the natural log of 3. So now we have x minus 2 is equal to the natural log of 6 over the natural log of 3. And then final step is to add 2. And isn't this what I had to type into the calculator to get the approximate form anyway? So your answer for x is natural log of 6 over the natural log of 3 plus 2. This is a way students would use if calculators were going to be used, because now you can just use natural log instead of having to do the change of base formula.
Well, you basically did.
Yeah, we did. So just another way of doing it. So what I'm getting at, do you always have to use the same logarithm that would cancel the base to solve these? And the answer is no. You can. I mean, here we use the log base 3 because I had a base of 3. But weren't we able to solve this really using natural log? We could have used common log. So let's do a few more. Part B.
Oh, that wasn't a part B.
Oh, part C for you then. Let's do 2 times. No, we already did a base of 3. Let's do a base of 5. 5 to the x minus 1 plus 4 equals 16. Remember, first step is to isolate the exponential term. The exponential term does not include the coefficient. The exponential term is just 5 to the x minus 1, so that needs to be isolated. So we got to get rid of the coefficient and we got to get rid of the plus 4, but it has to be done in the right order. You can't just get rid of anything you want in any order. Subtract 4 first. So now you have 2 times 5 to the x minus 1 is equal to 12. What gets rid of that coefficient? Dividing, yep. Dividing by 2. Now we have 5. X minus 1 is equal to 6.
I have a question. Do you only want us to use division to if we're doing
You can use it if you want. It'd be just as fine. What most students do on the University of, or Utah Valley University is just use this same logarithm, because calculators aren't allowed. So it would be more common to use a log base 5, and that's fine. Log base 5 on the left, log base 5 on the right. Log base 5 cancels that base of 5. So you have x minus 1 equals log base 5 of 6. And then you add 1.
So do you want us to write it with the log base, or can you write it with the
Either way. Either way is fine. This will be a perfectly acceptable form of the answer right there. Okay. Let's do example 2. Let's do one involving E. Example 2. If we're going to use E as a base, what logarithm are we going to use? Natural log. Okay. You finished? Bring it on up here. All right, then solve 6e to the 2x minus 1 equals 19. So what are we doing first? Adding 1, all right.
Do you have to choose 19?
Yes.
Can you do like...
No. Is it freaking you out because it doesn't divide evenly?
Yeah.
Why does that freak you out?
It's annoying.
You guys are prejudiced, and I won't stand for it.
That sucks, because it's going to happen anyways.
Fractions are people too.
No, they're not. No, it's not. If you take a fraction of a person, they're 10% of a person.
Yes, it is.
No, it's not. It's half of a person.
You guys have fractions of a brain, but I still say that you have a brain.
Shut up. That was hard stuff.
All right, anyway. What are we doing now? Besides acting like a bunch of sissies for fractions, you divide by 6.
I'm done with this.
So now we have e to the 2x equals 20 over 6, which is indeed 10 thirds.
Why?
Oh, fractions. I'm going to die.
Damn.
Now you understand no big deal.
No, I don't.
Yeah, you do.
Fractions, I'm going to die. Hey, I'm going to text my friends. Fractions. Hey, I'm going to text my friends. Fractions, I hate them. What's going on Twitter? Fractions. That's what you guys are like, right? What gets rid of the base of e?
Natural log.
Natural log. Okay. Natural log cancels a base of e. So what we have is 2x equals natural log of 10 thirds.
Oh, that wasn't too bad.
No.
Because we don't have to solve it.
Now what?
Divided by.
So x is equal to the natural log of 10 thirds all over 2. What was the big deal there?
The fractions.
No big deal. No big deal.
I love like having problems like this and showing it to my like 8-year-old sister and she's
Like, so they're like, I don't want to.
they're like, oh.
Okay. That's really as bad as it gets for exponentials. Logarithmic equations are going to take a little bit more time. So, here we go. Let's get into logarithms. Logarithmic equations. It's not that these are more difficult, there's just more variations on what they look like. There's more variations on how to solve them. So we're going to have to do a few more examples of logarithmic equations than we did for exponentials. Now, think about this. Answer this question. If logarithms were the inverse of exponentials, then what's the inverse of a logarithm? Exponential. So if I give you a logarithmic equation, what undoes the logarithm function? An exponential function. Any exponential function? If I have a log base 2, can I get rid of that with any base? No. This one, we do have to use specific bases here. So let's do example 3. After I list the steps, and you write down the steps, they're very similar to the steps for exponential. For exponential, we isolated the exponential term. So for logarithms, we're going to isolate the logarithmic term. Isolate the logarithmic term. Now put something in parentheses here. This may include condensing multiple logarithms. Okay. If you have multiple logarithms on the same side of an equal sign, you have to condense them into a single logarithm, then isolate it. Step 2. This is a funky word. Exponentiate both sides of the equation. Exponentiate means you raise, or you put a base on both sides, basically. Whatever expressions are there, those become exponents. Hey, BJ?
Hey, did you do?
Oh, I thought we got that on recording.
Nope. Pause that one. Step 3. Solve for the variable. Bless. Okay. Example 3, part A, solve log base 4 of x plus 2. Now notice the x plus 2 is inside the logarithm function, so put it in parentheses. Okay. Minus 4 equal to negative 2. Now, I guess there's like a pre-step to step 1. You really ought to decide on what your answers are even going to look like before solving. What I mean is domain. Are there values of x that simply will not work? Because the reason I'm telling you this, you do end up with extraneous solutions sometimes with logarithms. Negative 2 won't work. What else won't work for x? Anything below negative 2. It may happen that we get an answer for x like x equals negative 10. Would that even make sense for this problem? No. So you really ought to consider the domain of the logarithm, because you will end up with extraneous solutions on these, just like when we solve radical equations. Just keep that in mind. Anyway, isolate the logarithmic term. That includes the logarithm and what's inside the logarithm. So here we have this logarithmic term, log base 4 of x plus 2. That's the term that needs to be isolated. So you add 4. So we have the log base 4 of x plus 2 equals 2. I do see on a number of occasions a lot of students trying to do this. Well, now I got to subtract the 2 over here. Does that work? No. Yeah, that plus 2 is inside of a logarithm. Doesn't work. You can't minus that 2 until the logarithm's gone. So we've done step 1. We've isolated the logarithmic term. Step 2, exponentiate. That doesn't mean raise both sides to a power. That means these become powers, and you have to put a base. Which base are we going to use here? Base of 4. Okay, exponentiate means you put a base and allow these expressions to become exponents. Okay, so if you have a base of 4 and then the exponent is a log base 4, those cancel each other out. So on the left side you just have x plus 2. On the right side you have 4 squared, which is 16. So that was step 2, exponentiate both sides. Step 3, solve for the variable. These are pretty easy, aren't they? X equals 14. Now, just ask yourself, does that fit in the domain of that logarithm? Yeah. And these really aren't that hard to check either.
That question, so if it doesn't fit in it, what would you say?
No solution. Okay. Let's check this. Plug 14 back in there for x. Let's see if this even works. If you plug in a 14 for x and add 2, what's the log base 4 of 16? It's 2. And what's 2 minus 4? Negative 2. Okay? These really aren't that hard to check. You ought to get into the habit of checking these. Okay? Matter of fact, let's go back. Go back. Let's do part B of example 1. This was our solution, correct? These aren't quite as easy to check in your head, but you still can check these. What if we took this as our solution and plugged it back in for that to check our answer? What we would have is 5 to the log base 5 of 6 plus 1 minus 1, and that's supposed to equal what? It's supposed to equal 6, right? Well, does it? 5 cancels the log base 5, right? Now the 6 is no longer an exponent. It's just an expression. 6 plus 1 minus 1 is supposed to equal 6. Is that true?
Yeah.
Yeah, because those cancel. So those aren't that bad to check either. It's worth it to take the time to check these. So, part B, same example. Exponentials do not, no, because the domain of exponentials is all real numbers. But the domain of logarithms is restricted, so you do quite often end up with extraneous solutions. Okay, you ready? Negative 2 times the log of x minus 1 is equal, I don't want to do too large of a power here, we're going to be careful. Alright, let's do negative 4. Let's first decide on the domain. Before we even start solving this, what are some values of x that simply will not work? What can x equal? X can't be 1 or anything below that. So if we get an answer that's less than 1, either we've made a mistake, that could have happened, either we made a mistake or the answer is just extraneous. So Just keep that in mind. All right, what do we do here?
Divide by negative 2.
So I've heard two options, both of which actually would work. We've got to decide which would be, I'm not going to say the best, but maybe the quickest. One option is to move this back up as an exponent. That would work. It actually would work. I'll be honest with you, that's probably not the easiest way. What is this negative 2 doing to the logarithm? Multiplying it. So to undo that, we could divide by negative 2. This really would be the quicker way to do this problem.
Question.
Yeah.
So why, when it's in front of it, it's just multiplying it, but when it's like squaring it, or when it's like up as an exponent, it's like squaring it? Why is that? Like, why does that work?
I can show you the proof of that here in a second after we finish this.
It's going to be a lot. Please don't answer it. It's going to be confusing. Please don't answer it.
Not really, no.
Okay.
Where were we? I'm lost here. Oh, we just divided. So what we have on that left side is x minus 1. We really don't need the parentheses anymore because there's no function that it's inside of. And on the right side, actually, we didn't get rid of the logarithm yet. It's going to say we have an exponentiator. I'm telling you lies. It's just like you guys tell me, yeah, BYU's awesome. That's lies.
Hey. And that's like lies.
What's that?
That's Texas, boy.
You said D.
Come on, man. Come on. We're all friends.
No!
I did, didn't I?
You said that Utah friends and BYU friends are like logarithms and radicals.
That is true.
It's very near to you.
That is true. Now that I think about it, I actually can't stand the side of you BYU fans. Okay, anyway.
I mean, I don't have to learn this?
Yes.
Oh, sweet.
Step 2. Exponentiate both sides using base of 10. Where the heck did that 10 come from? This common logarithm has base 10. Okay? Base of 10 cancels a log base 10 as long as that logarithm is an exponent. And I still see this. Every year I see this, you guys. Take a look up here. Do these cancel each other out?
No.
This is a 10 and that's a log base 10.
But it's not raised to the log.
It has to be a base of 10 raised to a log base 10. Those cancel each other. I see that mistake all the time. Just be aware. So now we have x minus 1 all by itself. 10 squared is 100. Add 1 to both sides. X equals 101. Okay. Again, really easy to check. If you took 101 and plugged it in there for x, subtract 1, it's 100. Log 100 is 2. 2 times negative 2 is negative 4. Okay? These are some of the more simple logarithmic equations. Let's do example 4. Let's get a little bit harder. Multiple logarithms. Multiple logarithms. Here we go. What?
That looks like 100.
That's 101.
I know that, but it looks like 100.
Oh, sorry. Log of x plus 2 plus log of x minus 1 equals 1. So if you look back at what I had you write for step 1, this may include condensing, keyword there, condensing, multiple logarithms. Okay? So this is referring back to last time's lesson, 4.4. Why did we learn about condensing logarithms? It's for this purpose. And really, at least for this class, this is the only purpose for learning how to condense logarithms, is to solve logarithmic equations. If there's a plus sign between two logarithms that have the same base, it's important that they have the same base, otherwise you can't condense them. But if there's a plus sign between them, how do you condense? The expressions inside multiply. So condensing this becomes log of x plus 2 times x minus 1.
Would it be easier
We are going to FOIL that here in a second.
It would be easier to FOIL it.
We are going to, yeah. So now we have a single logarithm. The only way to solve logarithmic equations is to have a single logarithm, not multiple. And now we can get rid of that logarithm using a base of 10 on both sides. So now we have the expression x plus 2 times x minus 1 is equal to 10. Oh boy. What type of equation is this going to turn out to be? Quadratic. Now, think back. What are our options for solving a quadratic equation? How do we solve a quadratic equation? Factoring. Quadratic formula. We could complete the square. We could use square roots if there's no linear term. Let's see what works here. Factor or FOIL this together, you're going to get x squared, and then we're going to have minus x plus 2x minus 2 equals 10. That turns into x squared plus x minus 2 equals 10. Subtract 10 on both sides, and you have x squared plus x minus 12 equals 0. And yeah, that factors into x plus 4 times x minus 3 equals 0. So the solutions, or I'm going to say potential solution, are x equals -4 and x equals 3. The reason I'm saying potential solutions, anybody know it's a problem? You guys hear that? If we tried to take each one separately and test it, x equals -4, if we plug that in, where'd you go? Here we go. If we plugged in -4 here, or even to over there, you can't take a logarithm of something that's negative. It doesn't matter that the number itself is negative. It's if you plug it back in and the argument becomes negative. -4 plus 2 is still -2. -4 minus 1 is still -5. That's no good. X equals -4 is extraneous. Are you listening carefully? If you forget to check on a test and one of the answers happens to be extraneous, you will lose points because it's not technically the correct answer. Okay? Now, you still have to check +3. Does +3 work?
Yeah.
Check them on both logarithms. Here 3 plus 2 is 5, that's fine. 3 minus 1 is 2, that's fine. So 3 is okay. The only solution is x equals 3. Okay? Let's try same example, part B. I gotta challenge you guys. It's way too easy.
Yep.
It is, isn't it? Why is math so easy all the time?
Do not say that ever again.
Here we go.
Because that is an invalid argument.
If I say it, it's always true.
No.
If something comes out of my mouth, you can take it to the bank.
BYU is better than Utah.
See, that came out of your mouth. Nobody trusts you.
I trust you, Andy.
Thank you.
I trust you too.
Thank you.
I don't know.
I can speak on witnesses. And we have this on recording.
Yeah. And this is recording as well.
Come on now.
Look, it's like, wow.
That'd be super weird. Oh.
Ooh, this is going to be a good one. I can already tell.
I'm just excited.
Oh boy.
Got a question for you. If I got an answer of -2, would that work?
No.
If I got an answer of -5, would that work? No. If I got an answer of 1, would that work? An answer of 1? It works here, but it doesn't work here. So just some things to keep in mind. Now, we have to condense these two logarithms. The problem is there's a minus sign. I guess it's not really a problem. It's a difference. We're taking the difference of two logarithms. So how do we condense it? Division. So we're going to have log base 5. Now we have to form the quotient of x plus 1 over x minus 1. And that is equal to 2. Okay. Now we get rid of the logarithm. Now we're on step 2 of the steps. Step 2 is get rid of logarithms. So we're going to use a base of 5. We're going to exponentiate both sides. So now we have the rational equation, x plus 1 over x minus 1 equals 25. Now, we talked about how to solve rational equations way back. First of the year, first week, matter of fact, when we were studying for the Accuplacer, we did a few of these. So it's been a while. How do we do it? It's not exactly the way we did it, no.
Do you make the bases or the bottom the same, correct? So that you do like
Actually, you know what? No, wait a minute. We could. There's I can think of 4 different ways actually that we learned this. I think I showed you a couple of different ways. Actually, Valerie, I think Valerie had a pretty good idea. Instead of 25, couldn't we think about that as 25 over 1?
Well, and then can you make the bases the same?
That's one way to do it. You could times it by x minus 1 over x minus 1. And then if the denominators are the same, then you solve what's in the numerator. That's one way to do it. But if you have one single fraction that equals one single fraction, there's usually
Can you jump up Kate to the front office?
Okay.
Thank you.
Yeah.
I was going to say cross multiply, by the way.
Yeah. That's what you were talking about, right, Valerie?
Yes.
So we're going to take this x minus 1, cross multiply it up there. Then we're going to take this x plus 1, cross multiply it down there. So 25x minus 25 is equal to x plus 1.
Can I have Timmy to the attendance office for a minute, please?
Yeah. They said 1 minute, Tui. They said 1 minute. You better run.
They said a minute actually.
That's 1 minute.
No, but yes, but they said a minute, not 1 minute.
Get your facts right.
They said 1 minute. So anyway, add 25, subtract x, 24x is equal to 26.
What'd you do?
Use values.
Valery's theorem.
Yes. Can we make that a thing? I'll make a poster.
Did you discover it?
Obviously.
Did I tell you about that student from Lehigh that came up with his own theorem?
Are you kidding?
Brock. His name's Brock.
Brock.
We're calling it Brock's theorem.
Oh, yeah, I remember that.
We're going to learn about it in February, actually. It's on the schedule.
Dude, how old is he?
It's pretty cool. He came and described it to us last time. Simplify the expression. X equals. How do you simplify that?
26 over 24?
13, 12. Now, is that a valid answer? Is that in the domain or is that out of the domain?
That is valid.
What is the approximate value of 13 twelfths, by the way? It's a little larger than 1. So if we took something a little larger than 1 and plugged it into either logarithm, is it okay?
Yeah.
And I'm more concerned about this one here, the second logarithm. Something larger than 1 minus 1 is something a little larger than 0, so it's okay. So that one seems to work. X equals 13 twelfths. All right. Example 4, 5, 10. Example 5. Okay. Log base 2 of 2x plus 4 equals log base 2 of x plus 8. Oh, Now they're on opposite sides of the equal sign.
Then you subtract it and then you divide, and it equals 0.
It can equal 0.
Yeah, it can.
Yeah.
Wait a minute. We got a couple of good suggestions here.
I like mine.
Why was that?
So, the suggestion was made, I can't remember who made it now, but what if we subtracted this? Was the suggestion made to subtract? Who said it? Was it you? Well, a couple of people were yelling it out. So what if we subtracted this entire logarithm to the other side? Okay. Log base 2 of 2x plus 4 minus log base 2 of x plus 8. Now what does it equal? It equals 0. Now we can condense these into a single logarithm, log base 2 of the quotient 2x plus 4 over x plus 8. And that's equal to 0. Now we can exponentiate both sides, put a base of 2. 2 to the log base 2 cancel each other out. So now we have 2x plus 4 over x plus 8 equals 2 to the 0, which is 1. I know we're a little short on time, sorry. Now I thought I heard somebody mention this last time. I was going to throw a fit. Did somebody say, well, just use the fish method? And I think it was Aubrey. Didn't you? Admit it.
I don't know. I don't know.
Oh, don't ever say that. Fish method is so easy.
I don't even remember 5 minutes ago.
Don't mention it. It's an unmentionable thing. Cross multiply. So 2x plus 4 equals x plus 8. Now, I'm going to tell you this is the absolute longest and weirdest way to solve this equation.
Okay, you serious? I just got the answer.
Everybody stop. Look at where we are now, and look at where we started. Let me get...
Oh my god.
Are you kidding?
I just wanted to see how long you guys would go along with this.
Are you kidding?
Look at where we are now. We have 2x plus 4 equals x plus 8. And look at where we started. Does anybody see anything?
Yeah, you lost.
Sorry, we're getting so much time. Let's use
Now, you guys apparently like to do things the long and the hard way, but if this were me, I would just go like this. Well, if I use a base of 2 over here and a base of 2 over there, what happens? Those cancel each other out.
I could have told you that.
I'm going to write a letter.
But your suggestions were wonderful. Thank you for suggesting that. Either way, we're at the same spot. 2x plus 4 equals x plus 8. So what does x equal?
4.
X equals 4.
Those are
Pretty cool, huh?
not really.
You guys are so silly. Let's do this the absolute longest way possible. Now, I noticed I left one problem off for objective 1, solving exponentials. I'm sorry.
No.
So we do have to go back and do one more exponential problem.
I think we understand.
No, you don't.
That's one of
I'm
them.
pretty sure.
Example 6. All right, then if you understand, then you solve this one all by yourself.
Great. One of us can solve it by ourselves.
This is another exponential. Solve the equation e to the 2x minus e to the x minus 6 equals 0. That is true. We've done equations with multiple logarithms. We haven't really looked at multiple exponential expressions.
I got one step compound and I'm lost.
Don't you just add that in? The X.
I'm like, it's what?
If you were multiplying these two times together, you could.
Oh, okay, okay. So that's
Alright,
But that doesn't apply here. So
Don't you just condense it?
it's a little bit different than you think, you guys. It actually involves a principle that you're going to use a whole heck of a lot next year in AP Calculus that you may have seen, you may not have seen. It's called U. Raise your hand if you're familiar with the idea of U substitution. A few of you know what I'm talking about. Use a lot of it in calculus, which you're all taking next year, by the way. I want you to write this. I want you to let U equal e to the x. Now, something else you have to really get good at looking for, you guys, this term right here, e to the 2x, we need to rearrange that a little bit. Do you agree that it's the same thing as this? Are those the same thing?
Yeah.
They are. If you have a power being raised to a power, you just multiply the powers together, so you end up with 2x. So instead of thinking of that first term like this, you ought to think about it like this. Y like this. Now it's u squared. And what does the middle term become? U. So this equation just becomes u squared minus u minus 6 is equal to 0. Why is that form of the equation better than what we started with? What's more simple about it? It's a quadratic that is solved easily by factoring. Okay, this factors into u minus 3 and u plus 2 is equal to 0. And then that means u equals positive 3 and u equals negative 2. But we're not solving for u. We don't care what u equals. We want to know what x equals. Now what do we do? Yeah, we already know what u equals. U equals e to the x. So now we have two separate equations. E to the x is equal to 3, and then e to the x is also equal to negative 2. Now we have two smaller equations that are much easier to solve than the original equation we started with. So how do we solve this? Natural log cancels a base of e, so natural log here, natural log there. So x is equal to the natural log of 3. That's one of your solutions. Do the same thing over here. So x is equal to the natural log. Uh-oh. Say that again. Exactly. Did you guys hear that? This one's no good. So the only answer is x equals natural log of 3. That's called u substitution. We'll do a little bit of it here in this class, but a lot of it when you're doing integrals next year in calculus. Okay, so let me go back to my checklist. Checklist. We did this one. We did that one. Uh-oh. Darn it. You see the need for a checklist? I would have not remembered that we hadn't done that.
Dang it.
You should have made them in the
So, compound.
Yes.
Compound interest. We have one more example. This is the last one. If you've forgotten the formula for compound interest, that's a shame, because you need to remember for the test. A equals PERT, principal, times e to the rate times time. This is the compound interest. Continually, I guess. This is continually, or continuous. Continuous compound interest. Yeah?
Isn't there another equation that's like a equals p times 1 minus?
Yeah, that's for normal compound. This is continuous. The one you're talking about is a equals p 1 plus r over n to the nt. You don't need to know this one.
Okay, good.
You need to know this one. That's continually compounding interest.
Wouldn't the other one be considered simple interest then?
That's not simple interest, no. That's still compound interest, just not continually compounding.
What's the difference?
Simple interest is interest that's
No,
accrued
it's
just
different.
once.
The difference between continuous and not continuous.
Compound interest would be, well, we're going to accrue the interest monthly,
So it's
or we're going to accrue the interest quarterly. That's just compounded. Simple interest is, I loan you $1,000, you pay me back with 10% interest. That'd be $1,100. That's simple interest. But if I say I'm going to accrue the interest monthly, then the interest compounds every month. But continual compound interest is the interest is always accruing at every moment of time, instead of accruing it regularly. Does that make sense? And it really actually isn't that big of a difference. Continual versus like monthly, it ends up being a few dozen dollars. It's not that much. Anyway, continuous compound interest. Example 7. Suppose you want your $10,000 investment to double in 10 years' time. So you're investing $10,000, and this is assuming that you just invest that lump sum. You don't make any future deposits. It's just you leave it alone into some kind of an account, a mutual fund or something. Suppose you want your $10,000 investment to double in 10 years' time. If the interest is compounded continuously what does the interest rate need to be? So you know you're going to leave it in there for 10 years. You know you make a principal investment of $10,000. What we don't know is the rate. We don't know R. So because this is compounded continuously, that word continuously should let us know we're going to use this formula. A equals principal times E to the rate times time. Now, what do we know? What do we not know?
We know what A is. We know what P is.
Exactly. I was just going to get to that. Did they explicitly tell us what the value of A is, the future amount? No, but implicitly it says, well, it's going to double, so 10,000 becomes 20,000. So we do know the future value of this investment, 20,000. We know the principal investment is 10,000. The value of T, what does T stand for? Time. So we need to fill in what we do know and then solve for what we don't. 20,000 equals 10,000 times E to the unknown value of R, which we don't know, and that's going to be multiplied by 10. Because the variable that we're solving for is in the exponent, what type of equation is this? Exponential. So in order to solve an exponential, we use logarithms. Specifically, if this has a base of e, we're going to use natural log. Now, we already know the steps. You isolate the exponential term. This is the exponential term right here, e to the r times 10. So we got to isolate it. And we divide by 10,000. Okay, so now we have the equation 2 equals e to the rate times 10. And then we take natural log. Natural log cancels base of e. So we have the natural log of 2 is equal to the rate times 10. And then we divide by 10. Yep. Divide by 10. So the interest rate is natural log of 2 over 10. Now, I want you all to go to the bank and say, I want you to make my interest rate natural log of 2 divided by 10.
I'll do it.
And they would say, huh? No, actually, bankers are pretty smart.
And you have to figure it out without a calculator.
Yeah. They would probably know what you're talking about. Now, we do have to, unfortunately, leave it in that form because we don't use calculators. But if you're interested, what is the natural log of 2 divided by 10? Well, if you
69. Oh, 69.
so if you turn this on, let's see, natural log of 2, and then
Oh,
divide that by 10, it's 0.069. So it's roughly 7%, which is, that's actually a really good interest rate. You don't usually see that high of an interest rate, but anyway, there you go. You guys know what CDs are? Banks, CDs, certificate of deposit. They never ever have interest rates that high, 7%. Right now, CDs, ooh, they're probably below 2%. I mean, they're really low interest rate. If you're wanting to have substantial gains in money, don't use CDs. CDs are safe. Okay. If you invest in a CD, it's not like you're going to lose money. You don't gain a ton. If you invest in a mutual fund, yeah, they do have higher returns, but also, what's the flip side?
High risk of losing money.
There's a risk of losing money because it's in the stock market and it fluctuates. So this is also assuming that whatever account you're putting it into has that same interest rate for the 10 years. So it must be some kind of a bond or a CD or something. I don't know. Because mutual funds don't have a constant interest rate. Anyway, that's it.